Today, we will study the remaining assumptions of the method of least squares. Assumption number 4 tells that the variances, the conditional variance of the error term will be the same. Technically, this is known as homoscedasticity. Homo mean equal and scedasticity mean variation, which means that variance for different UIs will remain the same, and that will be equal to sigma square. That is, variance of U1 will be equal to variance of U2 will be equal to variance of U3 and so on, and that will be equal to variance of Ui, which will be equal to sigma square. This is called homoscedasticity. Before applying ordinary least square technique, we have to verify that variances of error term conditional variances, because if we look at this one, this is variance of Ui for the given value of xi, which means that this is the conditional variance of Ui for the given value of xi, which is equal to expected value of Ui minus expected value of Ui given xi whole square. And as we know that mean of the Ui is 0, so we will put it 0, and we will get expected value of Ui for the given value of xi square, expected value of Ui square for the given value of xi, which is equal to sigma square. And technically, this is known as homoscedasticity. So the variance of the Ui will be homoscedastic. That is variance of Ui for the given value of xi, that is equal to sigma square. We can also display it in the following figure. These are the values of x1. This is the variation. These are the variations, and as it is clear from this figure that for the given value of x1, for the given value of x3, and so on, variance of the error term, that is the error, that is the observed values, that is the observed, that is the predicted, and similarly this one. So this difference and this difference, this is nothing but the error, and when we square it, we will get the variance. So by squaring, we will have this curve. For the second value of x2, we have the same variance, and so on, which means that for each given value of xi, the probability density of Ui having the same variance Ui. Now, this is heteroscedasticity. This one is homo because the variances are same. And if we look at this figure, so it is clear that in the first For the first value of x1, the probability, this is the probability density. You can see that there is a much variation, and second case the spread is little bit flattened, and in the third one it is more flattened, which means that the variances will be different. So this is called heteroscedasticity. If the variances of, say, if the variance of, let me write it, variance of u1, that will be equal to sigma 1 square. This will be in in symbol, but we haven't any Latin symbol in the toolbox, so I wrote it in words. Similarly, variance of u2, that is equal to sigma 2 sigma 2 will be in subscript and that is square, and so on. Variance of un, that is will be equal to u1 u2 will be in subscript. Similarly, sigma will be in Greek letters, sigma square, sigma n will be in subscript, and square will be in power. So in this case, variances of u1 u2 and un will be not the same, but they will be different. Variance of the u1 is sigma 1 square, variance of u2 is sigma 2 square, and variance of un is sigma n square. And this is technically known as the homoscedasticity. It can be also seen from this figure. The next assumption is that of the no autocorrelation between the disturbance. Given any two x values, we have two values, different x values, that is xi and xj. It is written in the braces that I is not equal to j. The correlation between any two ui and uj is 0. Symbolically, covariance of ui uj for the given value of xi xj, which is equal to expected value of ui minus its mean, which is expected value of xi ui, sorry, for the given value of xi. Similarly, uj minus conditional mean of uj, which is expected value of uj for the given value of xj. Now, expected value of ui for the given value of xj, xi, sorry, and uaj divided by xj and y. Y. So it is clear, or we studied that this term expected value of ui for the given value of xi, it is nothing but the mean of the ui, and we proved it that it is 0. Similarly, this term expected value of uj for the given value of xj, this is also the mean of the term, which is 0. So we will get expected value of ui for the given value of xi, and in the second step, sorry, and second we will get uj, this is uj, and this is given value of xj. So this is uj and xj. Why? Because mean of the error term, let me write it, that y so because expected value of ui for the given value of xi and expected value of uj for the given value of xj, that is equals to 0. That is conditional means of ui and uj are equal to 0. And as we know that formula for covariance, that is if we have two variable x and y, so we can its formula is x minus mean of x, and mean of x is nothing but expected value of x, and similarly y minus expected value of y, this one. Now you can compare this formula with the above one, as these are conditional means. So in the above case, we will write expected of ui for the given value of xi, as this is the conditional means. Otherwise, the two formulas are very much similar. Just replace x for the ui and yj for the y, that is expected value of ui, expected value of x minus expected value of x, and for the expected value of x, just replace it with the conditional mean of the ui for the given value of xi. Otherwise, this is just the normal formula in of the covariance. Now, in this assumption, we are saying that no autocorrelation between the disturbance. So, if we write down correlation between, autocorrelation is nothing but the correlation between the two variables. So, the formula for the correlation is correlation of xy, which is equal to covariance of xy, and in the denominator we have standard deviation of x multiplied by standard deviation of y. This is the correlation. Now you can see that if correlation, if we are saying that there is no autocorrelation between two disturbance terms, which means that covariance of xy that will equal to 0. So covariance of, which means that covariance of xy divided by standard deviation of x and standard deviation of y, that will be equals to 0. Now look at this term. Now this is equal to 0, which means that either covariance of x will be 0 or standard deviation of x and standard deviation will be 0. These two will never be 0, as there will be variation between the values of x and values of y. So these two cannot be 0, which means that covariance of xy will be 0. So if we are saying that there is no correlation between the two error terms, so it means that alternatively we can say that the covariance between the error terms are 0. So here it is in equation 3.2.5, that covariance of ui and uj is equal to 0. When covariance becomes 0, then correlation will be also equal to 0. So this is the assumption number 5, that no autocorrelation between the disturbance term. The disturbance term will be independent of each other. If in any case you find out that the disturbance term are correlated, then in such a case we will not be able to use the method of the ordinary least square to find out the coefficients of beta 1 and beta 2. Now it is also displayed in the figure that in the first figure there is a correlation, and this is a positive serial correlation. In the second case, this is the negative serial correlation, and in the first case there is no auto correlation or serial correlation. Assumption 6, In assumption 6, we are saying that there is a zero covariance between ui and xi, that is expected value of ui xi equal to 0. Formally, covariance of ui xi, again this is the formula for the covariance, and again expected value of ui, that becomes 0. So we have expected value of ui, this ui expected value of ui is 0, and ui multiplied by xi minus expected value of xi. So ui multiplied with x, ui multiplied with expected value of ui xi and expected value of ui and expected value of xi. Since xi is not stochastic, as we read out in the previous lecture, that in the regression context, independent variable be non-stochastic and dependent variable be stochastic, which means that expected value of ui, that is 0, because we cannot apply expectation on a non-random term. So expected value of xi, that would be equal to x, and expected value of ui, this is 0. So the second term will be 0. So you will get expected value of ui divided by xi, which is 0, and this is by assumption. We also stated that expected value of ui and xi is 0, as it is written over here, that expected value of ui and xi equal to 0. In 7 assumption, the number of observation n must be greater than the number of parameters to be estimated, which means that if you have 2 parameters in a regression line, then the number of observation will be greater than 2. If we have 3 parameters in a regression, then the number of observation in both x and y must be greater than 3, and so on. Assumption number 8, variability in xy. There will be variation in the x values as we study the hypothetical example of 60 families, and we see that the income of different families were from 80 and 100 and so on. Assumption number 9, that the regression line will be correctly specified. There will be no specification bias. And this assumption will be studied in a separate chapter, that what is specification bias. The specification bias having many forms. There may be specification bias in the functional form. Sometimes we may ignore the important variable. In other cases, we may include an irrelevant variable in the model. So all of these are come in the specification bias, and there is a separate chapter in the book. Let me write it down here, that specification bias or error in functional form. Sometimes we need we need x in a model, but we include x square in it. So and so on, or 1 over x instead of x, and so on. So these are all error in functional form. Another form of the specification bias, that sometimes we ignore an important variable from the model. So this is again specification bias. Number third, sometimes or in some situation we include an irrelevant in some situation we include an irrelevant variable in the model. So again, this is an example of the specification bias, and so on. So we will study in full detail. A full chapter is available in Gujrati. Just remember that the specification and specification bias, there may be error in functional form. We may include an we may include an irrelevant variable in the model, or we may drop an important variable in the model. So there may be other specification biases and will be discussed in detail in the coming chapter. So this is assumption number 9, that the model, there will be no specification bias in the model. Now look at this figure. This is unemployment rate on the x-axis, and this is the rate of change of money, wages. So here it is the two functional form. One is y equal to alpha plus alpha 2 xi, another is beta 1 plus beta 2 1 over xi. So if you need that the unemployment rate and the rate of change of money, wages, this is an economic relationship, and you can search it in the Google, that what is the functional form between these two. It will usually follow the nonlinear Philip curve. So this is the nonlinear Philip curve, and on the other hand, this is the linear. So if you need the linear curve, and instead of fitting the linear model, you fit the nonlinear Philip curve. So this will come in the category of changing the functional form of the regression. In the non-linear Philip curve, yi equal to beta 1 plus beta 2 1 over xi, and in the second one, alpha 1 plus alpha 2 is xi. In the first case, if we did a variable 1 over xi, and by mistake we fit it as xi, so this is a mistake in the functional form and will come in the category of specification bias. As well as, if you look at the two forms, the nonlinear Philip curve model is linear in parameter but not linear in the variable. On the other hand, the linear curve, that is both linear in parameters and variable. So these are two curves. One is linear Philip curve and the other one is nonlinear Philip curves. Okay, next. Here is an example that what is multicollinearity, and this is our assumption 10, that there will be no perfect multicollinearity. That is, there are no perfect linear relationship among the explanatory variables. By explanatory variable, we mean that the independent variable. So the independent variable will not be in the linear relationship with each other. And if we find it that the two variables, the two explanatory or the two independent variable are in linear relationship among each other, then we will not be able to find out the estimates of the regression model, and there will be an error in fitting that model. Now there is an example of multicollinearity. Remember that multicollinearity is associated with the multiple regression, because in the simple linear regression model we have only one independent variable. So there is no concept of multicollinearity in that case. Multicollinearity is the problem of the multiple regression when we have more than one explanatory or independent variable in the model. Look at the table. These are the y values. We have the x1, x2 and x3 values. So if we look at x1, so x1 is, if we multiply x2, it is also written over here. So if we multiply x2 with 2, so 2 2s are 4 and plus 1, that is 5. Similarly, if we multiply this 4 with 2, so 4 2s are 8 plus 2, that is 10. The function mathematical structure is written over here. Similarly, if we do multiply 5 with 2, so you will get 10 and plus 1, that is x1, 11, and so on, which means that x1 is linearly associated with x2 and x3. So this is an example of the perfect multicollinearity. And if you run the regression, that is, if you run the model, that is y equal to b1 plus b2 x1 plus b2, sorry, b2 x1 b3 x2 and plus b4 x3, sorry, this is, sorry, this is beta naught, let me write it again, b1, this is actually b1 x1 plus b2 x2 and plus b3 x3. If you run this regression, so this is your task. Try this model in any software. You will find out that the value of beta 1, beta 2 and beta 3. You cannot find out these three estimates because x1 is linearly related with the x2 and x3. So this is called perfect multicollinearity. So whenever you run the regression, so confirm it that there will be no perfect multicollinearity between the explanatory variable. And there is again a full chapter, even a full segment or a full section devoted to the multicollinearity in this book. And I think that multicollinearity we will study it in the next semester. Okay. Now here are some mathematical formulas. VAR stand for the variance, SE for standard error. Sigma square is constant homoscedastic variance of UI. Sigma the standard error of estimate. So sigma hat that is equal to summation UI hat square divided by n minus 2. Summation UI hat square, which is equal to summation yi square minus summation xi whole square divided by summation xi. And remember that these are small xi and small y. So these are in deviation forms. You cannot find out that by usual values of x and y because small xi this is equal to capital X minus mean of x. Sorry. Similarly, small yi this is equal to capital Y and minus mean of capital Y. So note that this small yi and this small xi similarly in the denominator we have summation xi square. So this is not a usual summation xi square, but this is a deviation form. So if you need to find out xi and small yi, so the first thing that you have to find out xi by x minus mean, and if you want to find out small yi which is equal to y minus mean, and after that multiply these two, sum it and then square it. Similarly, variance of beta 2 hat, this is equal to sigma square divided by summation xi square. Again, xi is in deviation form, and the value of sigma square can be find out here. Similarly, standard error of beta 2 hat, just taking square root on the above variance of beta 2 hat. What is variance of beta 1 hat? Here it is its formula. So now look at here. This xi is in capital form, and in the denominator x, this is in deviation form. Similarly, standard error of beta 1 hat, this is equal to just taking square root on the variance of beta 1 hat, and in the last we have covariance of beta 1 hat and beta 2 hat, which is equal to minus x bar, and variance of beta 2 hat, which is equal to minus x bar sigma square divided by summation xi square, because variance of beta 2 hat is equal to sigma square divided by summation xi square. So just put the value of variance of beta 2 hat here. So you will get sigma square divided by summation xi square. Now here it is, the Gauss-Markov theorem. This is a famous Markov theorem, and the Gauss-Markov theorem or Gauss-Markov theorem, this is also known as the blue property of the OLS estimator. Blue stand for bislinear unbiased estimator. When you obtain beta 1 hat and beta 2 hat, so beta 1 hat and beta 2 hat will be the blue. This is known as the Gauss-Markov theorem. By blue mean that beta 1 hat and beta 2 hat will be linear. There will be linear. That is a linear function of the random variable such as the dependent variable y in the regression model. In the second case, it will be unbiased. That is, expected value of beta 2 hat will be equal to beta 2, and expected value of beta 1 hat will be equal to beta 1. And in the third one, variances of beta 1 hat and beta 2 hat will be minimum, or we can say that they will be efficient estimator. What is an efficient estimator? An efficient estimator is that one that having the minimum variance. And we suppose that we have two estimators, say T1 and T2. Now, if variance of T1 is less than variance of T2, then T1 is said to be an efficient estimator, say of mu. So this is called efficiency